Patricia Carroll from the Connections Committee. Professor Jordan Ellenberg grew up in Potomac, Maryland, a child of two statisticians. Very smart folks. He excelled in mathematics from a young age and competed for the U.S. in the International Mathematical Olympiad 3 times, winning 2 gold, 1 silver. Went to college at Harvard, got a master's degree in fiction writing from Johns Hopkins, then returned to Harvard for his PhD in math. After graduate school, he was a postdoc at Princeton. In 2004, he joined the faculty of UW-Madison. He is the Vilas Distinguished Achievement Professor of Mathematics and the John D. MacArthur Professor of Mathematics since 2015. In addition to his research articles, he has authored a novel, The Grasshopper King, which was a finalist for the 2004 Young Lions Fiction Award, the Do the Math column in Slate, the nonfiction book, How Not to Be Wrong, and many articles on mathematical topics in the New York Times, Washington Post, Boston Globe, Wired, Seed, and The Believer. So please welcome Professor Ellenberg.
Very good. You guys are going to find out I'm pretty loud to start with, so hopefully this won't be too loud. I'm just going to tell some stories about math today. That's what I usually do. I'm going to start on the slides, and then I actually have some sort of topical stories I want to tell, so I'm going to switch to the blackboard for topics that move too fast to have slides. But let me start. Patricia talked about college, so let's go back to college. I want to talk about a summer job I had when I was in college. I worked at a biological lab, and they asked me the following question. This was my job. Ready? It's right here on this slide. They asked me, how many people are going to have tuberculosis in the world in the year 2050? Now, I was in college back in around 1990, so 2050 seemed like an unimaginably long time away. Now it's uncomfortably close. So let me tell you, how I worked on this. So my boss gave me a big folder of papers, and again, I want to say this was 1990, so when I say a folder, I mean a manila folder, the thing there's a picture of on your screen right now, and then my kids don't know what it is, but it's the real thing. A big folder of papers all about tuberculosis, all about the way it spreads, all about contagions, all about the life cycle of the disease. All of this stuff broken down by age, by race, by sex, by nationality, by medication compliance. I mean, a big folder, lots of papers, right? Basically, everything that was known about the progression and the spread of this disease. And you take all that information and all that data, and you make what's called a model, right? You sort of program it into your computer, and you make a model of how you expect tuberculosis to behave. If you know the situation in one year, you can estimate what's going to be the situation in the next year, and then using that, you can estimate what the situation is going to be the year after that, and so on, right? So you run your model, you run it year after year, decade by decade, until the number on the screen says 2050, and then you're done, and there's a number on your screen, and I gave him a number, and then he paid me, and then that was the end of the summer. Okay, that was the end of the summer, but it's not really the end of the story. It wouldn't be such a great story if it were. I kept thinking about this problem, actually, and as I thought about it a little more, there was something that kind of troubled me, and what troubled me was this, that of course in any kind of study of any real-world situation, like the spread of a disease, there's a certain amount of uncertainty, right? If somebody says that under a certain circumstance in a certain country with patients under certain conditions, there's a 12% infection rate of tuberculosis, okay, what do you know? You probably know that the real rate under most circumstances is not going to be 2%. And you probably know it's not going to be 60%. But do you know it's going to be 12% on the nose? Do you know it's not going to be 10% or 14% or 9%? No, you probably don't know that, right? There's a little bit of uncertainty in each little element of your model. And what happens as you run your model year after year, decade after decade, is that whatever little uncertainty you have in each part feeds back upon itself. Right? It feeds back upon itself and grows. And you grow less and less certain over time. Those little error bars around your estimates grow wider and wider. And what I learned when I sort of looked again at what I had done through this point of view is that by kind of making different choices, in each case like fairly close to what the data suggested, I can make almost anything happen. I can make it be the case that tuberculosis didn't exist in 2050, and I can make it be the case that we all had tuberculosis in 2050. So the real answer to this question was that I had no idea how many people are going to have tuberculosis. Yeah?
Are you assuming that there'd be no advances in medicine?
That's a great question. So of course we don't know what's going to happen in medicine. So now it's a long time ago, but as I recall, that was not built in, right? So it was sort of saying under what we know now about how to treat the disease. Because you're absolutely right that there's sort of, okay, so we got a lot of time, so if it's okay, just to like veer off into comments on comments. Vice President Dick Cheney, do you remember this guy? And by the way, a former graduate student at the University of Wisconsin-Madison, all but dissertation. He never finished his dissertation, so he didn't get the PhD. I always think we should like bring him back and like say, just write the dissertation. Anyway, I don't think he'll do it, but he was I think in history, I think he was a history grad student long ago and lived up in Eagle Heights and Shorewood Hills. Dick Cheney got a lot of heat for talking about known unknowns and unknown unknowns. People made fun of him like he was talking about sort of some kind of arcane philosophy, but he was making a real point that there's sort of, what I'm talking about here is known unknowns. We have some estimate that we got from a study and we can sort of guess about how far off that might be. But there are also unknown unknowns where there are just complete changes in the situation which we really don't know how to predict, and we can't say what's the probability that sort of somebody will completely cure tuberculosis tomorrow, right? We don't know. So that's it. So unknown unknowns are very hard to model, and in some sense we just have to kind of punt and say, yeah. Okay, end of digression. Anyway, where was I? My giant question mark. I had no idea how many people were going to have tuberculosis in the year 2050, and now here comes the poignant part of my story, because I went back to my boss. It was now fall, but I went back to my boss, and I was like, listen, I feel like in good conscience I should tell you that I no longer have confidence in this number that I gave you back in August. And here's what's interesting. My boss totally did not care. He was like, look, I wanted your best guess. You gave me your best guess. Like, that's it. So I found this like rather frustrating, actually, because I know that guy like went around giving lots of talks, and he's like, here's our best guess as to how many people are going to have tuberculosis in the year 2050. And if somebody asked him, like, well, where does that number come from? He would say, like, well, I like hired some guy and he did the math. Okay, so what I really want to talk about today is kind of mathematics as, the art of asking questions. Here, in some sense, we saw a situation where maybe I was asked the wrong question, or maybe you sort of have to respond to the question with a question. One way I learned about this most, and this is actually the story I start my book with, is this gentleman right here, also a famous statistician like my mom and dad. This fellow is called Abraham Wald. So this guy is a mathematician and a statistician. He works as part of the statistical research group during World War II. So this is the sort of top secret collection of some of the greatest mathematical and statistical minds at the time who were gathered in a little apartment near Columbia University in order to sort of work on statistical problems related to the conduct of the war. So in a way, it was kind of like the Manhattan Project, except it was actually in Manhattan. That's what. So one day, a group of high-ranking military officers came to the SRG, came to this group where Abraham Wald worked, and they said, we're trying to figure out something about how to armor are planes. So you know, when a plane comes back from flying a mission over Germany, it looks something like this, right? I mean, it's sort of riddled with bullet holes. But they had observed something quite interesting, which is that the pattern of bullet holes was not uniform across the whole body of the plane. So here's a little mini table. They saw, for instance, that there were fewer bullet holes in the area of the engine and more bullet holes in the area of the fuselage. So here's the question that they brought to Abraham Wald and the statisticians there in that apartment. They said, how much more armor should we be putting on the parts of the plane that are getting hit more? You know, we could just we can't load the whole plane with super heavy armor because then the plane won't fly, and that's bad. But obviously you want the plane to be protected, and you want the protection to go where it's needed most. So they said there's got to be some kind of a math formula for this, smart guys. Tell us what we should be. That's my imitation of a Army general. How did I do? Okay, so you can see that my mathematical background is richer than my military background. Okay. They said, how much more armor should we be putting on the fuselage and the places where there are more bullet holes? And the answer that Abraham Wald gave them was not the one that they expected. Wald said, the answer is no. You should be putting the armor where the bullet holes are not. All right, let's stop and sit with that for a minute, because that was not what the generals expected to hear. You should put the armor where the bullet holes are not. And Wald explained to them, because you see, it's not that the Germans can't hit your planes in the engines. It's that the planes that got hit in the engines are the ones that are not coming back from Germany. When you say it, it makes sense, right? So this is an example of what we call in statistics selection bias, that, again, the question they were being asked was not quite the right question. And the mathematician's job in this scenario was hopefully to answer the question with a question, right? To sort of say what assumptions are embedded in the question that you presented. In this case, the assumption is a rather subtle one, the assumption that the planes that you are seeing when they return for a mission are in some sense like a random sample of all planes that left. But of course we know that that's definitely not the case. And when you think about it for a moment, there's some very good reasons that that's not the case. There's a lot of examples of this kind of thinking I could talk about, but let me tell this one. Continuing, maybe this whole talk will just be about bearded Jewish people of the mid-century. My ancestors. This, who are we looking at here? This person is not a mathematician, not exactly. This is a rabbi, Rabbi Dov Weissmandl. And he was famous for studying, he was a 20th century rabbi. He was famous for studying what are called equidistant letter sequences in the Torah. All right, so let's talk about what that means. So let me give you an example. It's sort of characteristic of this kind of slightly fringy branch of Jewish numerology that Weissmandl was interested in. Okay, so in the book of Esther, I think do I have a picture of this? I don't have a picture of exactly the same thing. In the book of Esther, there are 12,196 letters. Okay? Suppose you start with the very third letter in the entire Torah, which is the Hebrew letter Aleph, which kind of makes like a vowel kind of a sound. If you count forward 12,196 letters from that, so that's the exact length of the book of Esther, the next letter you find in the Torah, imagine how much spare time these guys had. Well, anyway, and the next letter you see is the Hebrew letter Samech, which makes a kind of an S sound. And if you go 12,196 more letters from that, you get the letter Resh, which says kind of an R. So kind of like a, oh, I missed one, sorry, my notes. After the Samech, you get a Taf, which says T, and 12,196 letters after that, you get a Resh, which says R. So T, R. That's our Hebrew lesson of the day. That spells Esther. That spells Esther's name. Which again, remember, that number, where did we get it? It's the exact length of this book of Esther. And this is considered quite striking by the rabbis, right? Because in some sense, Esther's name, which is, I mean, in this biblical story, is like, you know, well after the Torah, is somehow already encoded in some sense, like in the letters of the Torah. And there's a big tradition of this kind of thing. I mean, as I said, Weizmantel is a 20th century rabbi. He's from the 40s and 50s. But there's a tradition that's much older than that. Here's, I have one, I didn't have an image of the exact equidistant letter sequence I showed you, but here's a different one where these letters, which you can kind of see are equally spaced, they spell out the word Torah. So there's the word Torah, there's the Torah like kind of talking about itself, being like, this is what you're reading, the Torah. So like I said, this is an old tradition in a kind of certain flavor of mystical Judaism, but as in so many other of our cultural practices, once computers get involved, everything changes. Because traditionally you do this by hand, right? I mean, if you're a kind of Kabbalistic rabbi in Poland in the 17th century, like, you know, you're counting with your hand. Let me show you the front page of a paper, Equidistant Letter Sequences in the Book of Genesis, so you can sort of see that this is much more contemporary. I think this comes out in, I didn't write down the date, I think it's 1990. It's a little too blurry to see. This is by 3 researchers in Israel, Doron Vitztum, Eliyahu Rips, and Yoav Rosenberg. And let me tell you about the experiment that they did. They chose 32 notable rabbis from history. And when I say history, I don't mean like biblical history. I mean like sort of like around medieval times to the present. So recorded history, ranging from Avraham HaMalach to the Yabez. So they have those names, and then they encoded the date of birth of each of these rabbis. So if there are any non-Hebrew speakers in the room, let me tell you that in Hebrew, numbers are actually encoded as letters. So Hebrew doesn't really use like digits per se. So the dates of birth of these rabbis, if you wrote them down as numbers, would actually be like a string of letters, like just like a name. Okay, so you have 2 sets of strings of characters. You have the names of the rabbis, and you have their dates of birth. And then what they do is for each of those rabbis, they say, let me see if I can find an equidistant letter sequence somewhere in the Torah spelling out that rabbi's name. Now, you might already think, boy, I'd be surprised to sort of find some sequence spelling out that rabbi's name. But really, you shouldn't be, because the Torah is a pretty long document. It's, in all, it has 304,805 characters. In modern terms, that's 2,178 tweets. So in that amount of space, there's really like a lot of places to look. And remember, you have freedom of like how large you want the space between the letters to be. And so with all those choices, it's actually not so surprising that you can find the names of these rabbis. And it's not so surprising that you can also find these dates of birth. And then what they did is try to find how close is each rabbi, I mean, encoded as an equidistant letter sequence, how close in the Torah is each rabbi to the date of their birth? They tend to appear on like the same portion of the Torah. They actually tested this in a rather clever way, which is that first they tested how well do the rabbis match their dates of birth. Then they said, well, let's scramble the dates of birth up randomly, so they're not matching the actual rabbis, and run the experiment again and see if the match gets better or worse. And they did this with, I think, about 1 million different permutations, these 32 dates. And you know, in some sense, if there was no relationship between where the rabbis' names were and where their particular birth date was, you would expect the actual matching to be, you know, sort of in the middle of all those different random permutations. But this was not the case. This was not the case. They found that the correct association of rabbis with their birth dates ranked, it had the 453rd highest score among the 1 million different matchings that they tried. Well, this was quite startling, right? I mean, let's step back a minute and sort of remember that we are talking about rabbis and their birth dates, which took place more than 1,000 years after the Torah was encoded and sort of placed into its final form. And yet, they found a correspondence that was much closer than chance would suggest. And according to the usual rules of statistical inference, I mean, this would lead us to conclude that something put those names and dates close together. And as you can see, this study was published in a quite reputable journal, Statistical Science. The journal this article ran, and the journal ran a rather unusual preface to that edition. I'll read it to you from the editor-in-chief. He said, "Our referees were baffled. Their prior beliefs made them think the book of Genesis could not possibly contain meaningful references to modern-day individuals, yet when the authors carried out additional analyses and checks, the effect persisted. The paper is thus offered to statistical science readers as a challenging puzzle." So in other words, the editors of this journal are saying, this result really makes no sense, but they played by the rules, so there's no real justification for us not publishing it, right? I mean, the sort of rules of statistics are what they are. They tell us like sort of what kind of conclusions that we license. And having followed those statistical rules, they could see no academically justifiable grounds for rejecting the paper. Now, as I said, these folks, they're mathematically trained and they followed the rules. But I want to emphasize that not everybody follows these same rigorous practices. So as soon as this paper got out and it got a little bit of attention, then people got super excited. And what happened very soon after that was there was a journalist named Michael Drosnin who found out about this, and he wrote a huge bestseller that you might have heard about called The Bible Code. And this really sort of blew up publicity on this. And Drosnin was not a mathematician, and he was not so interested in like obeying the usual rigorous rules of statistical analysis. And he was also not interested in sort of boring stuff like medieval rabbis and when they were born. He just went looking for sequences for every cool thing he could think of, and claiming that it was all predicted in the Torah. So he predicted all kinds of crazy things. He predicted the assassination of Yitzhak Rabin. I think that's what you see on the cover there. That was like his big marquee thing, these two sequences crossing. A comet hitting Jupiter. He went on Oprah Winfrey. He went on CNN. He mostly predicted stuff that had already happened. I want to emphasize, if you want to get in this game, that's definitely the way to do it. You should sort of take stuff that already happened and then sort of show how you predicted it. He did at one point predict the end of the world for 2006. So we sort of dodged a bullet on that one. Apparently, somehow that managed to not happen. And I just want to emphasize that, this sort of industry, Drosnin himself has kind of like receded a little bit. He wrote, I think, 3 of these books, but you can search for it today. Every time I do it, I find like sort of fun new stuff. There's still a sort of a thriving industry of people sort of freelance finding crazy codes. This was one I saw that the last time I searched for this, which I might just keep this slide because it raises a compelling question that we must all think about. Is Oprah the prophet Elijah? I'm not actually sure whether the Torah says yes or no, actually. I should look more deeply into this person's analysis. So okay. I don't want to like walk out. Oh, I have one more kind of cool slide to show you, like just what a bunch of these letter sequences look like. Let's all sort of enjoy this. So now it's printed in this nice font where everything's like very square, so you can really see the sort of diagonal lines joining different letters. Let me explain what we're looking at here. So one thing you have to keep in mind is that rabbis had a lot of names. They didn't have sort of social security cards like we do today. So here's one. There's a guy called Rabbi Avraham ben Dov Ber Friedman, who was an 18th century Hasidic mystic. Okay, that's kind of a mouthful. So like, what does he go by on the street? Like, he's called in the Vidstum paper, he's called alternately Rabbi Avraham or Hamalach. But in real life, he was also called Rabbi Avraham Hamalach. Like, why not use that? It's not clear. They made choices about which names of the rabbis to use. And that gives you a little bit of wiggle room. It would be like if we were doing this analysis today and we wanted to write about like Dwayne "The Rock" Johnson, like the famous movie star, if we were trying to find his birth date. We could call him Dwayne Johnson or The Rock or Dwayne "The Rock" Johnson or DTR Johnson. We would have a lot of choices. And for each of these rabbis, they have a lot of choices. And what people found, so I'm going to talk about the work of of Brendan Mackay and Dror Barnatan, who were two mathematicians who kind of interrogated this work, they found that this kind of wiggle room, these kinds of choices, actually lead to drastic changes in the quality of the results. So they said if those original researchers had called this guy Rabbi Abraham Hamalach instead of calling him just Hamalach, then all of a sudden their results don't look so good. So out of all the different choices they could have made, somehow they made the choices that made the results look the very best. Now, here we get into sort of delicate ground because nobody really knows. Well, I can tell you what Barnatan thinks. Barnatan thinks these guys cooked the books. I don't know. Maybe they did, maybe they didn't. You can kind of fool yourself sometimes, like into sort of saying, like, well, this choice works best, and now I see why it was really the right choice to have made. You know what I mean? Like, so I've talked to these guys too, and maybe I'm just nice, but they don't seem like charlatans to me. I think they seem like people who sincerely think of their protocol as correct. But nobody really now thinks this. And maybe this was what I'm showing you right now is actually a very compelling example. So McKay and Dornatan picked an alternate list of names for the rabbis. They made an alternate set of choices. They checked it with the theological authorities at the Hebrew University of Jerusalem, and they said, this is just as good of a name from a biblical point of view. This is just as good of a set of names. And when they tried those names and matched them with the dates of birth, they found something quite startling. They found, well, look what you see here. You see that actually, well, of course, I haven't told you what the different colors mean, but you see a lot of letter sequences that are crossing and are very close to each other. They actually found they got even better performance, even better matching of names to dates. With one small wrinkle, with one small change, which is that this is not the Torah, this is the Hebrew edition of War and Peace that you're looking at here. Maybe you guys all noticed that already, I don't know. So what can this mean? Not, I hasten to say, that Leo Tolstoy wrote his novel intending in such a way that when it was later translated into Hebrew, like it would contain the name of all these rabbis, like, no, it just means that if you have this amount of wiggle room, just as when you have these sort of small errors in the tuberculosis things that kind of multiply and feed back onto each other, in the same way, if you have these sort of small choices that you can make for the names of each of these rabbis, these little choices that you make when you put them all together, they can actually balloon into a huge amount of freedom that you have to make the data say anything you want. So this is an area where a result that seemed extremely compelling, so compelling that it was published in a journal, is later seen to be like, if not empty, like highly questionable. And I mean, you could do this with essentially any text and any list of names if you give yourself enough freedom to choose the names in such a way that it makes the result work best. Okay, so many different stories I could tell. I think I won't talk about stockbrokers. I can talk about stockbrokers afterwards if we want. You know, again, something to be careful about when we think about results that seem incredibly compelling. Let me sort of tell a story. You might have heard this one. So there was a statistical model that was developed by the guest marketing analytics team at Target, a store we all shop at. And this algorithm, which sort of takes data from people's loyalty cards, right? People who are sort of shopping and sort of keeps track of what they buy and et cetera, it concluded that one of its customers, who was a teenage girl in Minnesota, was pregnant. Okay, whence the picture I'm showing you. And they started sending this girl like coupons for like baby gear in the mail. Well, her dad was super PO, as you can imagine. He like called up Target and was like, this is like super offensive to me, like my daughter's not pregnant and you're like sending her all this stuff. And then the daughter was like, well, Dad, actually I am pregnant. That was the So, you know, what do we take from this? I think people heard the story and it's a little bit spooky, right? That, you know, you can fool your parents, but you can't fool your Target loyalty card. But I would say I want to counsel, and we're going to kind of transition into here into like giving like my little spiel about like the age of big data and what does it actually mean. I'm going to try to make the case that companies do not know more about you than you yourself know about yourself, or more about you than your parents know. And again, one thing I want to bring back is that this is like a little bit like the Abraham Wald story, because we all hear this story about this crazy case in which Target figured out that the Target was sending the baby gear and stroller coupons to this girl whose dad didn't even know she was pregnant. We don't hear about all the baby coupons that were sent to people who are actually not pregnant, right? We don't hear about all the coupons sent to like 75-year-old men who happen to be buying the same kind of stuff that maybe pregnant women buy. I mean, we don't hear about that. So without seeing what the cases that we see, again, are sort of a selected set, not a random sample. Data is not magic. Target does not actually know who's pregnant and who's not. But that's not to say the whole thing is a scam, right? Because I emphasize, Target doesn't have to know with 100% acuity who's pregnant or who's not. If you run a big company like that, you are very happy if you can make your algorithm just do like 1% better than just guessing, or 5% better, right? That translates, at the scale that a company like Target is operating, that translates into real money. So I kind of want to chart a middle course where I'm telling you the age of big data, it is incredibly important, and the problems that people are working on are hard and do have real results, but they're not spooky. You shouldn't think of it as like Facebook knows who you are. You should think of it as like Facebook is trying very, very hard to make like 1% better guesses than it otherwise would, which to you, you probably wouldn't even notice, but to them translates into actual money. It translates into they can charge more for their ads, and that's where their revenue comes from. So let's talk a little bit about, I wanted to sort of close this part of the talk by trying to distinguish between different kinds of problems and how they're affected by data. So here's one kind of problem that we encounter in the natural world is like trying to understand the orbits of planets. And this is a problem where data is just great, because if you know like where a bunch of celestial bodies are at one position, and you know how fast they're moving, and you know something about how heavy they are, you can predict with extremely good acuity where those things are going to be for essentially the entire rest of astronomical time, for eons in the future. You know what I mean? If you want to know when Halley's Comet is coming back, I mean, you know when it's coming back. You know what day it's coming back. And not just the next time, but like the next 100 times in the future. And the more accurate you can measure, the more accurately you know. Let me, by contrast, I think the last time I gave this talk actually was like this. So what are you looking at here? You're looking at a 10-day weather forecast, except, guys, I have some bad news for you. You're not actually looking at a 10-day weather forecast, because there's no such thing as a 10-day weather forecast. Now, a television network will show you one, because people want them, so they're happy to look at it. But typically, we really don't know what the weather is going to be 10 days in advance. And that's because the weather is a fundamentally different kind of system from the motion of planets. It's what's called a chaotic dynamical system, which means that a very small imprecision in what we can measure now, even if we have a lot of sensors, even if the sensors are very good, unlike with the planets, its nature is that those uncertainties are going to feed back into each other, get bigger and bigger until, on a relatively short time scale, we really have no idea what the weather is going to be at a specific time in the future. Now, again, not saying weather prediction is a scam. It's not a scam. It's a real thing. It's gotten way better with time. I think the first 24-hour weather prediction was done by, I think it was in the 40s. It was in ENIAC. It was crunching the differential equations that control the weather. It did a 24-hour weather prediction, and it took about 24 hours to do. So that was not so useful. I mean, by the time it was finished, it was sort of saying, this is what I think happened. Like, you stick ENIAC's head out the window and see, like, was it right? They just reproduced that same computation on a Nokia phone, and it took about 8 seconds. So there's huge differences in computer power. And also, we can, in fact, go much farther. So it used to be that there was no such thing as a 5-day weather prediction. Now 5-day weather predictions are under most conditions actually pretty good. But the chaotic nature of the dynamics of the weather mean that there is actually a hard physical limit. Doesn't matter how big your computer is, doesn't matter how fast it is, doesn't matter how good your sensors are, doesn't matter how much data you have. There is a limit, and it's not very long, to how many days in the future we can predict the weather. Now, I've talked to various people about this, and there's not a total consensus on where that is. But I think I'll say this. I think I've never met anybody who thinks that we'll ever be able to predict the weather a month in advance. Doesn't matter how big your computer is, doesn't matter how much data you use, the chaos just takes over. People argue about whether the limit's like more like 2 weeks or more like, maybe you can get closer to a month, but nobody thinks you can do 30 days out. So, this principle, I have to share my favorite slide. This principle was made very popular by the movie Jurassic Park, if anybody saw this, where Jeff Goldblum talks about, who plays the scientist in the movie, the chaos theorist. This is not a still from the movie. This is an oil painting of somebody made of Jeff Goldblum with a butterfly on his finger that I dislike. So, Jeff Goldblum explains this principle that a very small change in the present conditions, like a butterfly flapping its wing, can create a tornado or a hurricane 2 weeks or 3 weeks later, right? These very small changes can have very big effects down the line, and that's what makes long-term weather prediction effectively impossible. By the way, here's another story I'm not going to tell today, but it's a very interesting one. That this movie was really popular in advanced military intellectual circles in the 90s when it came out, and the military response to this circle of ideas around chaos theory was very interesting. They were it was discovered that this principle, gosh, a butterfly flapping its wings can create a hurricane around the world 3 weeks later. And people were like, get me that butterfly. Okay, that's not how it works. I want to emphasize. That's sort of the point. But there is some understanding to it, right? I think that's an example of understanding the power of math, but not its limits. And to really sort of understand what we're dealing with as we go into this age of big data, I think we really have to keep our eye on both. So maybe I'll talk a little bit about a problem that I like. So I said the weather is a lot harder than the planets, right? Different kind of system. On the other hand, maybe I'll quickly show you the next slide. Maybe I should put these in the other order. On the other hand, the weather is governed by differential equations like this. These equations might be hard to solve, but there is an actual physical model for how the weather is going to behave. We might not be able to compute it in any reasonable amount of time, but it is in principle determined. On the other hand, a lot of data problems, like the one we saw with Target, and probably most of the ones that people care most about, are not about planets, and they're not about weather. They're not about purely physical systems governed by differential equations at all. They're about humans and human behavior. So if you thought the weather was hard, this is way more hard, right? If you're trying to understand what's going to happen in an election, which is what we're going to talk about in a minute, or an even simpler problem like what movie are you going to like? So what you're looking at here is a screenshot from Netflix. This is actually from my Netflix, because I was just watching Freaks and Geeks with my son, one of the greatest television dramas ever aired. And sort of part of Netflix's business model is to be able to correctly guess what movies you're going to like so that it can recommend things to you and that you're hopefully satisfied and want to keep watching Netflix, right? Because they want to keep you on their site. And just again, how many of you guys use Netflix or another streaming service like this to watch content? Okay, so you've probably noticed the recommendations are okay, but I think very few people are ever like, Netflix knows me better than my own spouse. They truly have seen into my heart and known exactly what I'm going to like. No, it's not like that. If you want my opinion, it will never and can never be like that. I don't think that's actually a solvable problem in that sense. On the other hand, they had a wonderful contest where they invited scientists from around the world. They said, we'll give $1 million to anybody who could improve our recommendations by 10%. make people sort of like agree with them 10% more often. This is now about like 8 or 9 years ago. I was writing an article about this for Wired magazine, and I got to interview their chief technical officer. And I said, I mean, 10%, it doesn't sound like, why are you offering like so much money for this? And he was like, you fool, you should be asking, why am I offering so little money for this? Like, why are you guys willing to work for so cheap? I mean, a 10% improvement is worth a lot more than $1 million to Netflix. And instead of having to hire people to do it, they're essentially temping it out. So again, this is when I sort of came to understand that at the scale these guys are working at, something that maybe does not sound so impressive to us, improving the ability of recommendation systems by 10%, actually means a lot of money to them and is something like well worth their while. So let me say a few lessons I learned from this. And here's one big one. This is what I sort of say to our students, and when we talk at the university, we talk to businesses a lot who are trying to sort of get more dataized. Here's kind of an amazing thing that happened in this contest. So they launched it. They're like, here's the data set. Like, see if you can improve our data by 10%. Something quite startling happened that people were able to improve about 7% in a couple days. In a couple days. Because in some sense, and people didn't use sort of like super new hardcore methods. They used kind of standard old-fashioned methods, and even those gave like a serious improvement. So one thing I sort of say to our students and one thing I say to businesses when they consult with us is like, everybody kind of wants the latest and greatest advance in artificial intelligence, machine learning. I actually think there's like a lot of math that's a lot more basic than that still has not been taken up by a lot of the business community, and a lot of gain would be found there. I mean, if there are any like, I'll say one technical thing, which is that Google is Google because those guys knew a little bit of linear algebra. They knew what an eigenvalue was. I don't know if anybody in the room likes to talk about eigenvalues, but it's something that we teach our like sophomores at UW. And the person who knew what that was, like, they made Google. That's it. It wasn't super fancy, actually. Okay. So that's one principle. I talk to people when they talk about data in their business. Another is to mix different ideas together. So the first part of the Netflix prize is that they get 7% improvement in like a couple days. Then the next part of the Netflix prize is it takes another 2 years to get to 10%. So they hit some kind of a wall, and what actually happens as people stumble over the line is that, you think sometimes the public image of math is that just some person kind of sitting in the room has some genius idea, and that makes everything better. In practice, math is often not like that, and what happened here is more typical, that basically all these people were working on it, all these people were getting incremental improvements, and what they found is, hey, if I have my way of doing it, and you have your way of doing it, which is totally different, and then we just do something very simple. We just take my predictions and we take your predictions, and we average them. That often did better than either one did separately. And in the end, how they finally got to 10% was sort of some massive agglomeration of, I think, about 28 or 30 different researchers who sort of all mixed their algorithms together and sort of turned the knobs and found the proportions that sort of gave the best results. Now, this is a little weird, right? Because in life, if you asked a bunch of people for advice, you would probably, like, take the best advice. You wouldn't say, like, okay, this person gave me advice that seems really good, and this person gave me advice that seems like not as good, so I should just kind of split the difference between those two things. That would be like a little bit weird. But that methodology actually seems to work surprisingly well for some of these data problems. And then to close, let me sort of give a slogan that sort of sums up what I've been trying to say about Target and about Netflix and about, I guess, Jeff Goldblum and his butterfly. People talk about data a lot, and I want to emphasize that it's not magic. It's not spooky. It's not psychic. It can't look into your mind. So that may sound like I'm diminishing it, but at the same time, I think businesses are essentially right to see it as an absolutely indispensable part of just about every business that there is, because of these incremental improvements that it can make and the way it can change what they do. So the metaphor I like is to say data is not magic, it's much more like electricity. It's something whose principles we actually do understand and can understand with science. That is, we are moving from an era where it was unknown to an area where it's going to be completely ubiquitous. We can basically understand how it works, but it's always going to be a little bit dangerous if you don't know what you're doing. So that's the end of my slides. You know what? Let's do this. It's 9:45. Let's take where's Patricia? Should we do like a little break and have questions? So what I want to do, I'm going to do something I don't always do, but I want to talk about legislative districting. And the reason I want to talk about that is because, one, the legislative districts that we sit in right now, right here in Wisconsin, are under challenge by the Supreme Court, and it's probably going to be decided like any day, they're saying, so we don't know what is going to happen, but maybe I should check my phone in the break to see if anything's out. And because it's probably like literally like the mathiest public policy issue like I've ever encountered in my days on this earth. But let's take a little break because I'm going to sort of switch gears and then move to the whiteboard. And I'll take questions. I'm going to have a drink, and like if people have other places to be, like they can like get up and stretch and move around or what have you. So hi everybody. Now I'm going to do more like what I do when I teach in UW, which is like write on a board. This whole slide thing has not quite come to the math department at UW-Madison yet. So it's I've learned to do it because if you talk to business groups and you write on a board, they think you didn't prepare. They're very upset. So I've had to learn to do it. But what I really like to do is like write on a chalkboard or a whiteboard or paper. And that's what I'm going to do now. So I just want to talk a little bit about this kind of red hot issue of redistricting and gerrymandering. It's an issue not just here in Wisconsin, although especially here, but in North Carolina and in Virginia and really all around the country. I organized a conference about this last fall, actually right after our case here in Wisconsin was discussed in the Supreme Court. And I learned a ton. I mean, and what I came out of it with is that I think mathematicians tend to see this as a math problem. Politicians tend to see it as a political problem. Lawyers tend to see it as a legal problem. It's really all three. And I think that any attempt to think about it without having all three of these things in mind is kind of doomed to fail. So I think there's just been a ton of like super exciting work that really involves people from all three communities, and I've learned a lot from talking to them. So I'm just going to try to sort of share a little bit about what I've learned and like what the basics are. So, okay, what is it? Well, as you may know, our laws in this state of Wisconsin are made by the state assembly and the state senate. I'm going to focus on, just so we don't get too confused, I'm going to focus on the assembly today. So our whole state is broken up into assembly districts. Okay, now ready? This is the quiz portion of our talk. How many assembly districts in the state of Wisconsin? Do you guys all know? Who knows it? Who knows it? That guy's really close. 99. Were you just going to keep on guessing numbers? No, okay. Okay, here's a really good one. Why is it 99 and not 100? This is like... So one good answer, which I think is not right, is you'd want an odd number so there's no ties. But lots of legislatures have even numbers of... So I don't think it's that. Why 99? Exactly, because the Constitution requires that the Senate districts be split up into 3 assembly districts. So the number of assembly districts is a multiple of 3. There's 33 senators, and there are 99 assembly districts, and 3 for each Senate. Those 99 districts, as is constitutionally required, have approximately the same population. I mean, they can't have exactly the same population just because things, that would be sort of too hard to arrange, but they need to have approximately the same situation because otherwise there would be like rampant unfairness, right? There would be sort of an assembly rep who had only 10 constituents and they would get an outside voice in the legislature. So, by the way, I should say, it wasn't always this way. The principle that the Constitution requires that all state legislative districts have the same population is from a Supreme Court case only in 1964. So before then, there actually were large differences, which were unfair, and that unfairness was removed by that Supreme Court decision. So many ways we could go. I will point out, having said that, it makes sense, right? All districts should have the same population. If you think about that for 1 second, you could be like, well, what does that mean? Does that mean they like the same number of human beings like live in that district? Does it mean the total voting age population? Does it just mean like the number of registered voters or like voters who are, or like people of that age who could be registered, but are U.S. citizens, so could register, whether they're registered or not. I mean, there's lots of different things you could mean, and those would actually all give you different answers for where the district line should be drawn. In fact, in case you're curious, Wisconsin, and I think almost all, if not all, U.S. states use total populations. So like, kids count in terms of, I think the theory being like kids and other people who don't vote are represented by that assembly rep, whether they can vote or not, and so sort of they should have their fair amount of representation. So that's the principle we use. But that's not constitutionally required, by the way, so that could change. Okay, so the districts are supposed to have relatively equal population, but of course, population changes and population moves. You guys probably know that, for instance, Dane County is the sort of site of some of the fastest population growth in the state, while the northern tier of the state is actually shrinking in population. It's not only not growing, the population is decreasing. So that means that the lines can't be static. You can't leave them where they are because some districts would become too small and some districts would become too big in terms of population. So every 10 years we have a census. The census establishes the official population figures, and using those figures, we do what's called redistricting. We draw new districts to reflect, to equalize population and to reflect where the population now is. As I said, this Supreme Court decision in 1964, Reynolds versus Sims, that makes all the districts the same size, it was thought that this principle that's called one person, one vote, well, in 1964 they called it one man, one vote, now we call it one person, one vote, that this principle was enough to guarantee that people were fairly represented in the state legislature. And the story I want to tell today is that I think this practice called gerrymandering has really thrown that into question, and people are feeling like the principle of one person, one vote is not enough to guarantee fair representation. So let me give an example and write some numbers on the board, okay? So let's give an example of an imaginary state where there's two parties, the purple party and the orange party, and this state has 60, what do I have, purple and green? The purple party and the green party. There's 60 purple voters and there's 40 green voters in this state. Okay, I have to use like small numbers or else I get confused. So it's a small state, 100 people. And let's also state this state only has 5 legislative districts, okay? And I'm gonna write down 3 different ways that population could be split. So here's one. It could be that you have 3 districts that have 15 purple voters each, and then one with 7 and one with 8. And now I want all these districts to have the same size. There's 100 total voters in 5 districts, so each district should have 20, right? So it better be the case that then there's 5 green voters, 5, 5. These 2 districts all look the same. And then 13, and then 12. Okay, that's one scenario. Here's another one. 9, 9, 9, 17, 16. And then, so you must have like 11, 11, 11, 3, and 4. So here's a scenario where I have 3 pretty competitive districts, and then 2 that are, really like wildly, 30 square miles of purple surrounded by reality kind of districts that are very skewed one way or the other. And then let me, one more. It could be that just the completely homogeneous case in which each district exactly represents a slice of the population that has the same split of voters as does the whole state. So then it would be like every district would have 12 purples. And 8 greens. So what I want you to note is that every single one of these ways of splitting up the population obeys the principle of one person, one vote. In other words, in each case, every one of those 5 districts has 20 voters. So in some sense, each voter has like the same power. They're one of 20 voters in the district. On the other hand, you'll notice that in this state, which is 60% purple and 40% green, that's a pretty big variance, by the way. I mean, this is not what you'd call a swing state, right? I mean, a state which has a 60-40 advantage for one party is actually, in the context of American politics, like a pretty strongly skewed towards that party state. You can see that a lot of different things can happen, because in this scenario, the purple party has 3 seats in the legislature, and the green party has 2. In this scenario, The purple party has just 2 seats in the legislature, and the green party has 3 and holds the majority. And in this scenario, the purple party actually has all the seats in this legislature. So actually, before we go on and talk about the law or the politics or the math, actually let's take a moment, and I want to ask you, I'm not going to ask you to tell me, I'm going to ask you to think about it. How would you rank these from fairest to least fair? Like if you have to decide like which seems fair to you, kind of think about your answer. Let's take a minute. And then having started to think about it, and this is what I do this in class all the time, so I'm going to make you guys do it too. Just because you're not paying tuition doesn't mean I can't make you do stuff. If you could just turn to the person next to you, they have their opinion about this and you have yours, see how well you can kind of get them to sort of see it your way, and then we'll sort of see what we land on as we talk. So just so try to, I really want to hear you guys talking, so I know that you guys are thinking about it. Okay, I feel like it's quieting down a little bit. I always hate to cut this off. Like I should like go in the dining hall, like get a piece of pie or something. I don't know. It's no, it's okay. So let's. There was some wild gesticulating in the back, though. I saw it. That's how you know math is taking place. Okay, so let's do a poll. I want to know. Okay, let's ask like most fair. Who thinks this one is the most fair? Okay, who thinks this one is the most fair? And who thinks this one is the most fair? Okay, so I would say this is probably the most popular with like a reasonable minority in favor of this one, and nobody likes this one. Okay, who thinks, let's do least fair. Who thinks this one is the least fair? And who thinks this one is the least fair? And who thinks this one is the least fair? So that's pretty evenly split, actually. I think like these two are equally disliked. So I would say in this scenario, I would say this division of the votes is probably the most popular among this group. I would say that's a pretty frequent when I give this talk, but I want to emphasize that people actually really do give different answers. And one thing I want to kind of say is that it's not clear to me that there is, per se, a right answer to this question, but I'll talk a little bit about how people think about it. But maybe just so it's out there, okay, the ones people didn't like were this guy and this guy. So maybe somebody who didn't like each one can tell me what's wrong with it. So somebody who thought this was the worst, what's bad about it? Yeah, so what offends our mathematical nature about this one, as you said, is that the party that has the minority of the voter has the majority of the legislature. Could that happen in real life? It's happened right here in Wisconsin in recent memory. So that's certainly something that can happen. Okay, what's wrong? Somebody who didn't like this one, what's wrong with this one? Yeah, somehow this also sort of seems to fail to reflect something real about the electorate in this state, that a party that does actually represent a rather substantial minority of the citizens of the state has like literally no representation in the legislature at all. Could that happen? Well, if you know anybody who's a member of the actual Green Party, they could tell you that that could definitely happen, right? So certainly anyone who's a fan of a party other than Democratic or Republican would tell you it's certainly possible that a party with like some not insignificant amount of support like will be completely zeroed out in the state legislature. So, so this one is one thing that's appealing about this is I kind of cooked it so that the proportion of purple voters in this state is exactly 60%, and here the proportion of seats that they win is exactly 60%. So you might first say, well, I guess what should happen, maybe the ideal to strive for, is that the proportion of seats in the legislature should roughly match the proportion of votes in the state. That doesn't fly. That's actually a pretty bad idea for a couple of reasons. Like one, the Supreme Court has already considered this, and that's called proportional representation, and the Supreme Court has already said as a legal matter, no, you don't have a constitutional right to proportional representation. That's too strong of a standard, and that's not what we're going to impose. So that's a matter of settled law, that we can't ask our districts to obey that. Secondly, what you would find, let's say you were in a state where there was like 70% members of one party, and well, actually even a state with 60-40 in real life. So that's, I mean, maybe I should have had an example of this in my mind. It's not Wisconsin, right? Wisconsin is not 60-40 with respect to one party or another. Maybe a state like Maryland, where I'm from, which I think is probably close to 60-40 Democrats. I would say a Democratic presidential candidate usually wins there by about 20 points. It would actually be, if you wanted to draw legislative districts there that where 40% of them were Republican majority districts, it would be pretty hard. And you'd have to draw them like really weirdly and do a lot of extra work. Because in some sense, if you sort of, there's a lot of parts of a state which look like the whole state in miniature, right? So there's like lots of places in Maryland which are about 60% Democrat, 40% Republicans. You'd have to sort of do something rather non-geographic to sort of get proportional representation. So I hope I've convinced you that this problem is hard, that it's not very obvious to just look at it and say what's fair. And for that reason, I think courts have struggled with how to deal with this problem. Very few people will say it's not a problem. Very few people will say this seems fair. So in some sense you can identify what's unfair, but it's very hard to say what's fair, and as a result, there really hasn't been a compelling legal standard. So the last time this came before the Supreme Court, the Supreme Court, they could have said, this is just not a matter that, for the courts, it's a matter for states to work out politically. It's what's, in technical terms, non-justiciable. So they could have said that. They could have said, this is not really up to us. It's no federal constitutional issue. They didn't say that. They said the opposite. They said, this does impinge on people's constitutional right to vote, and so the Supreme Court and the US Constitution does have authority. But they also said, we can't figure out a standard to say what's fair and what's not fair. So in this particular case before us, we're not going to throw out the map that's objected to, but we're not going to say we can't throw out a map. We're just going to say we're not doing it right now, and hopefully later we'll figure out what to do. So the Supreme Court is now at that moment of being asked again to figure out what to do. And I just want to talk a little bit about, and this is not going to be so long, I just want to sort of say a little bit about what has changed and what we're doing mathematically to try to get better notions of what's fair. So this is a subject that's moving pretty fast, and one interesting feature is that, let me tell you first about a notion called the efficiency gap, which has the advantage that it's very simple. It has some disadvantages too, which I'll tell you about, but here's how it works. And it's very intuitive. You say, a party does not want to waste its votes. What does a wasted vote mean? Nobody likes to feel their vote is wasted, so there's no moral value attached to this, but mathematically what it might mean is that, well, any vote in a district that you lose doesn't help you get any seats in the legislature, so you can think of it as wasted. So these 5 green votes here, right? But also, any vote that is above what you need for a majority is also wasted. So actually, in the situation where it's 15-5, the purple party has wasted 5 votes, and so has the green party. Whereas here, the purple party has wasted 7 votes, and the green party has wasted only 3. Like another way to put it is that if you want to win a lot of districts, the way you would do it is by winning a lot of districts 11-9, right? Because that's the sort of most efficient way you can get a district without using up too many of your votes. And if you imagine sort of somebody after the fact drawing these districts, that's exactly what they would do. They would try to give themselves a lot of close wins. So, all right, ready? Let's add it up. So here, okay, there's 5 wasted votes, 5, 5, and then 7 here, and 8 here. So let's see, that's a total of 30. And if we add up the wasted votes for the Green Party, it's 5, 5, and 5, and then 3, and then 2. So 15 and 5 is 20. Okay, what happens here? Now the Green Party has been super efficient, right? They have all these 11-9 wins, so they only waste 1 vote in each of these. They only got 1 more than they needed. And then, in the districts that they lose, they like really lose. So they didn't throw away too many votes here. They only wasted 3 and 4, and so the number of wasted votes is just 10, whereas the Purple Party has wasted 9, 9, and 9. All these votes that almost got them a legislative seat but didn't. So let's see, 9 and 9 and 9 is 27. 27 and another 7 is 34. 34 and another 6 is 40. So the efficiency gap is the difference between how many votes are wasted by one and how many votes are wasted by the other. So you see here it's a lot larger. Like the red party has been drastically inefficient. On the other hand, look at this one. Here, the Purple Party is the efficient one. It's only wasted 2 votes in each of these things. So it's wasted 10, and the Green Party has wasted 8 every single time, and has wasted 40. So this efficiency gap gives a sort of very intuitive and compelling measure for sort of how good a job you did turning votes into seats, and somehow you see that your guys' feeling that these two were somehow bad is reflected in this fact that in both cases there's a very large efficiency gap, in this case favoring the Green Party, and in this case favoring the Purple Party. And here the efficiency gap is not 0, but it's like pretty small. And so in this case that was brought in Wisconsin, in which our 3-judge panel here in Wisconsin, like throughout our existing assembly maps that we have right now, because the efficiency gap was at the heart of the case. And there was a very, very clear story that the efficiency gaps of our current maps, in which, for instance, so in 2012, there was a scenario in which Democrats won the majority of the statewide vote, but were held to a minority in the assembly. And in each case, the efficiency gap of this map being drawn favors the Republicans who drew the map quite a lot. By the way, side note, here's the claim that I'm not making. It might sound like what I'm saying is, aha, using this efficiency gap, we can detect that the assembly map in Wisconsin was intentionally drawn to favor the Republicans. But that's not what I'm saying. We know that the assembly map in Wisconsin was drawn intentionally to protect Republicans, not because I did some kind of statistical magic, but because like people filed tons of Information Act requests and did tons of detective work. We actually have all the memos and we have all the emails, and like we know, because we know what people were saying to each other. People deposed and subpoenaed the people who actually made the maps, and so it's not a matter of sort of statistical inference. It's a matter of like, you can't actually hide that you did this. And maybe this is another good moment. If I'm talking about Wisconsin, I'm talking about Republicans drawing maps to advantage themselves. The last thing I want to do is make it sound like the Democratic Party is innocent of this kind of maneuvering. And in fact, I would say historically, whatever party has the power to do this will do it, which is why a lot of people feel that that power should be removed. So I mean, what's going on right now in the Supreme Court, in the development that I think probably most opponents of gerrymandering find promising, is that the Supreme Court sort of moved up on its docket a similar case in Maryland, which is a democratically gerrymandered state. And there's some speculation that the fact that they are sort of considering both those cases together is to sort of to give them political cover, so that it doesn't seem like they're sort of, so that if they do throw out these maps, it's sort of clear that they're trying to stamp out a practice that in fact both parties do when given the chance. So at this moment, I think there's little question that there's more Republican gerrymandering around the country than there is Democratic gerrymandering, but that's probably mostly because Republicans control more state legislatures right now. They had a good election in 2010, right after the census, and that sort of put them in a position to do so. Okay, second question you could raise is, hey, if this is just something that both parties do and they happen to be in power, why is it a big deal? Like, why isn't it just part of like the sort of sharp-elbowed political fracas that goes back and forth? That is very much the case that the State Solicitor General, Misha Zeitlin, made before the Supreme Court. That like, it was, he said, like, look, I'm not saying it's fair. I'm not saying it doesn't smell bad. I'm just saying that's politics, and politics is nasty business, and the Constitution doesn't say politicians can't be nasty and unfair. So why is that not a good argument? I think it's the best argument the state has, by the way. I think it's because gerrymandering now is qualitatively different from what it was. It's an old practice, but it's qualitatively different now. I had an interesting talk. If any of you guys know Kevin Kennedy, who is the head of the General Elections Board when there was a General Elections Board here in the state of Wisconsin, but he's a person who has been involved with elections in this state for a very long time. And he said there's no question that everybody did it, Democrats, Republicans, like when they were in charge. But the way this looked in the 80s was you'd have some like very nerdy individual with a giant map who was like very knowledgeable about the districts. And they would sort of like laboriously be like, let me try this. And they would sort of spend all night trying something. And maybe it would be a little better, and maybe it would be a little worse, and they would try something else. You know what I mean? So the practice was definitely undertaken. Now, you can try 10,000 maps in an hour, right? So the ability to really engineer the map very precisely to your advantage is much, much greater now than it was in the past. So I think that we are now looking at a scenario where people can build in advantages that will be much harder to dislodge. If that carries through to the next census cycle, it can become kind of a self-perpetuating thing in a way that I think was truly not the case. I mean, when Sandra Day O'Connor wrote about this in the 80s in her dissenting opinion, she did not think this was a big problem, and she felt like, look, this problem will take care of itself. Like sometimes one party will win and they'll stack the deck in their advantage. Sometimes the other party will win and they'll stack the deck in their advantage. Just as, okay, let's be honest, right? In politics, parties that are in control stack the deck in their advantage in lots of ways. They sort of direct more resources to groups that they think will favor them, make contributions, et cetera. So, but I do think that gerrymandering in 2018 is on a sort of more pernicious and more structural level than it has been in the past. Well, I'm tipping my hand as to how I think this case should come out. But, so, an interesting thing happened between when this case was heard by the panel here and what was heard by the Supreme Court, which is that the the people arguing against the state of Wisconsin largely stepped away from the sufficiency gap notion. I want to give you a couple reasons. One, to a mathematician, the sufficiency gap, okay, ready, I'm going to use one more technical math word. I already said eigenvalue, but I'm going to use one more technical math word. The sufficiency gap is discontinuous, which we don't like. Maybe it's a little bit like Jeff Goldblum and his butterfly. Here you have a situation where the Green Party has wasted almost no votes, and the Purple Party has wasted a lot. But a very slight shift, if this was like 11-9 instead of 9-11, would create a huge shift in the efficiency gap, right? So that's somehow, since of course you're talking about what's going to happen in the future, and we don't know exactly what's going to happen in the future, it means that our ability to predict, I mean, we can look at efficiency gaps in the past, but it's like a very sensitive to like very small swings. So another problem with the efficiency gap, okay, ready? Here's another pretty good argument made by Republicans who don't want the current maps to get thrown out. They would say, but look, gerrymandering or no gerrymandering, they would say, districts are going to look like this because we know that Democratic voters cluster in cities, cluster geographically together, and so you're going to have 80%, 85% Democratic districts in a way that you basically are not going to have 80%, 85% Republican districts. And if you look at any Wisconsin election, like you'll see that that's true. You'll see that the number of districts that will vote 80% Democratic is, there are some. You might be in one right now. If you're not, you're pretty near one. There are not, I mean, even in the heart of Waukesha, it's hard to find an 80% Republican ward. There are probably some, but there are not a lot. So what that means is that if you actually say, I demand that the efficiency gap be 0, it's probably not realistic. Like even if you, that's what I'm saying is, even if you didn't gerrymander, the efficiency gap would appear to favor Republicans. So that's what we call like organic free-range gerrymandering, where it kind of happens without anybody doing it on purpose, like because Democrats are concentrated in cities, Democrats are going to be disadvantaged in seats. And a statewide election in the state of Wisconsin in which 50% of the people voted Republican and 50% voted Democratic, the Republicans probably would have a small majority in legislative seats, even without any gerrymandering, because on the sufficiency gap metric, we would waste a lot of, I didn't say we as a state employee, obviously I don't have a political party, Democrats would waste a lot of votes like right here where we're standing right now, and Republicans would not. Okay, so let me just close by saying about a development that I'm super excited about. So, you know, I said people who are trying to game the system and get political advantage are able to do it much better than they used to be because of mathematical and computational advances. But I want to emphasize that also our ability to detect gerrymandering is also improved thanks to mathematical and computational advances. So some of the work I think is really great, and it's done by friends of mine who are down at Duke. And for me, it's like very exciting to see these, you know, a math paper comes up and I read it and it's math, and then I see it like being discussed by like the Supreme Court of Pennsylvania like a week later. Very exciting. They take the following approach, which I think eliminates a lot of these problems. They say, what if you just looked at a random map? What does that mean? Like, what's a random map of the state? Well, what you do is you take the map as it now is, and now comes the part of the talk where I try to draw a freehand map of the state of Wisconsin. I get better at this every time. I'm still not great. I never get Door County right. My Door County is always like misshapen, and somehow it's that's the hard. I find that's the hardest part. Anyway, and then you know it's broken up, and now I'll do really bad because I can't draw like the. And there's a lot of real small ones where the population is dense, right, in Madison and Milwaukee, and then you know you got to have a lot of space to get 20,000 people like up here, and you know there's Superior, there's St. Croix County, you know, et cetera, et cetera. It's a little denser here around Green Bay, Appleton. Okay, it is what it is. You take the map as it is, and then you sort of just say, okay, ready? Pick a random district that's on the boundary between, pick a random like ward or precinct that's on the boundary between two districts, and just flip it. Move it from one to another. Okay, if you sort of made this guy's population too big, then you sort of choose another random one and like move it to another district. And you just keep on doing this. You let your computer run for a long time. You do this 10,000 times, and you've really sort of changed your districting to a new one, which still has equal population, but is like, you sort of wandered away from your original district. And you can just do this as much as you want. You can just, I mean, these guys in their computer, they have, and they wrote a paper about Wisconsin, by the way, where they have like 10,000 possible maps, district maps of Wisconsin, all of which obey all the laws, all of which strive to like do the things that Wisconsin law asks districts to do, preserve county boundaries when possible, preserve municipality boundaries. In fact, they typically do those things better than our existing map because the program asks them to do that, whereas our existing map was asked to deliver as many Republican districts as possible, sort of in some sense independent of those considerations. And then you can be like, and then you can go back and look at an election that actually happened and say, in each of these 10,000 maps, how many seats would Republicans would have won, and how many seats would Democrats have won? So I'll draw you a picture. Okay, statistics fans, if I draw a number, and here's 50, which is an assembly majority, so here's 99, and here's 0, and if I take, let's say, the 2016 legislative election, in which Republicans had, I've forgotten, but a modest majority in the popular vote. I think they won like 53 or 54% of the popular vote in that election. And now I make a little bar chart of how many of these 10,000 random maps give each number of Republican seats. What's it going to look like? I mean, there's probably going to be nothing over here, right? If Republicans get 53% of the vote, they're probably not going to get like 2 seats, right? But they're probably going to, yes, I like your little finger moving, right? Like this, like maybe there's some most typical thing. Maybe the Republicans will typically get around 55 seats, and that'll be the most common thing. And then as you get farther from that, it'll be less. So it'll be like some kind of a bell curve type of a thing. And that's exactly what you see. It's pretty cool. So you really see that, like, this is sort of your way of saying, if there was no gerrymandering, if just like a sort of mindless machine, which was not trying to give one party an advantage or disadvantage, was drawing the maps, just trying to preserve the county boundaries and keep the population equal, et cetera, it doesn't mean there's an answer to how many seats one party should win. As you can see, like, a lot of different things could happen, but there's kind of a range, and some things are more possible than others. Okay, then you take this, and then you say, like, now, what happened with the existing map? And it's like, you know, it's over here. Okay, it's not over here because it's not 99, so I do this kind of badly. In fact, this is really like a lot narrower. It's like this. But it's, but the point is, you see again and again that the map that we actually have is far, far more Republican skewed than the random maps. And that, I think, is a much more statistically robust kind of way to think about this problem. It's the best way we have to answer the question, what might the map look like if there were no gerrymandering? So I mean, in essence, I would say that this is probably the closest we can come to answering this question of what would be fair, that we actually sort of offload the process. We ask a computer, which doesn't have a preference of parties, to generate lots of maps, and we say, well, maybe fair means that it's sort of like within the range of the kind of things that the computer might produce. So a couple of closing remarks. One, a natural thing that a mathematician might say is, well, why don't we just let the computer draw the maps then in the first place? Okay, it turns out, if you talk to the lawyers, there's like a lot of reasons that we don't do this. I think it's possible that it could be made legal. I mean, the authority for drawing the map inheres in the legislature, and I think it's possible that the legislature could just decide to pass a law saying this was the procedure. The political science people tell me that it's completely politically impossible, that it's not, that it would not be accepted, and I think that's right. So I think that the computer-drawn maps, I think we're never going to hand over the authority to draw these maps to the computers. I think they're sort of to be used as benchmarks, things that we test our maps against. So thing two is that this analysis actually allows us to answer like a lot more questions than efficiency gap can. So it's pretty cool. So for instance, this can tell you by just looking at these random maps, okay, what kind of percentage of the popular vote under current maps would Democrats have to win in order to win a majority of assembly seats. Now, we don't know that exactly, but this kind of simulation process can give you some good estimates. So I can tell you what they estimate, because I was just looking at this. So estimates, I told you that because of this city-country thing, under neutral maps, to get 50-50 in the assembly, you'd probably have to get Democrats with about 52, maybe 52, probably not 53 is too much, maybe like 51 or 52% of the votes. They have to win by 2 or 4 points. So there is a slight skew in favor of Republicans. That's natural. It's just based on where people live. On the other hand, on our map, it looks like in order to get 50-50 in the assembly, Democrats would have to win statewide by maybe 54 or 55%. So in a state like Wisconsin, it's a very tall order. Like, it's actually quite rare for either a Democrat or a Republican candidate to win a statewide election by this much. I don't think, let's see, I don't think in any, I don't remember Walker Burke, but I think in typically Scott Walker, when he's won election, I know in his recall election, he won by about 7%, certainly not this much. And that was considered like a pretty resounding victory. And it's pretty cool. You can even see it. So the last statewide election we had, which was just a couple of weeks ago, this election for the Supreme Court, that was a fairly resounding win by, well, it's officially a nonpartisan election, but by the candidate who all the Democrats voted for, won by 12 points, got 56% of the votes. The theory predicts that that should be enough for a Democratic majority. Indeed, a super nerdy guy I follow on Twitter actually broke down the entire statewide vote in this race by assembly districts and found that Rebecca Dallett, the more liberal candidate, won in 57 of our 99 assembly districts. And about 7 of those are within 2%. So it exactly conforms with the expectation that had Rebecca Dallett won maybe 54% of the vote instead of 56% of the vote, she probably would have won at about half the assembly district. So it sort of shows you that even an election which was, I think, seen by everyone as an extraordinarily good statewide election for Democrats, that would have been maybe just enough to give the Democrats like a modest assembly majority, like much smaller than the majority that the Republicans enjoy right now. So this stuff is great. I love it. The big question that we don't know and we'll know when some of these court decisions start to come down is this too complicated for the courts? And I think that's the real question. I mean, I think that when this was presented to the Supreme Court, this was called, well, I can't remember the words that I think it was Justice Alito used. He maybe called it gobbledygook, or like, I mean, it's not gobbledygook, but judges are not wrong that they want a legal standard that not just like the Supreme Court, who has this sort of huge army of incredibly well-trained clerks, but like judges in every court in the land, they want a legal standard that is going to be understandable and usable. And as math educators, I think this is like the only time in the history of Supreme Court that our particular skills have been useful, that we have to make sure we can explain this stuff clearly and publicly enough that it is not seen as gobbledygook, but is instead is seen as a rather appropriate and commonsensical approach to a difficult problem. That's what I'm trying to train myself to do. I hope I did it today. So thank you guys so much.
Do we have any questions for him? I'll walk around with Mike.
Has anyone proposed creating the maps retrospectively to get the proper proportion according to the popular vote?
Yes, the question is like, could we look at what has happened in past elections and draw the districts so that the seats, the proportion of seats would match the proportion of votes? And I think there, the answer is more legal than mathematical. Like if somebody tried to force the legislature to do that, the legislature would say, there's very clear case law saying we don't have to arrive at that outcome, so we're not going to do it. I mean, I think that's what they would say. So, I mean, it's really interesting when you study this stuff because like there's mathematical constraints, but there are also political constraints and there are also legal constraints, and they all matter. I think mathematicians tend to be like, well, let's like sort of ignore this like legal stuff and like just think about the math. Big mistake, big mistake. Then you get people right, and they do write these papers. It makes me tear my hair out where they're like, well, what if we just like do like a bunch of straight lines across the state? Like, no, you can't do that. You can't just like cut some town in half and like, I mean, anyway, mathematically it's great. Straight line, we love straight lines, but it's
Are there any states that have an outside group draw their districts? And is that realistic for us?
Yeah, so the question is, are there any states, well, when you say they have an outside group draw their districts, I don't know if there are states that have groups from outside the state draw their districts, but there are states that have groups which are hopefully, at least to some extent, outside politics that draw their districts. So I think the most well-known example of this is in Iowa, where they have a panel of retired judges. And, you know, judges have politics, but not as much as people who are like, it's not as close to politics as the people who are literally the people running in the next election deciding who their voters are going to be. So it's at least at one remove. And I think, you know, Iowa has the same kind of good government tradition that Wisconsin has historically had, and that, you know, many people aspire for us to have again. So I think there is like a lot of movement. And here's the interesting political development. In general, this Wisconsin case, because it's a Republican gerrymander that's being sued against. In general, if you look at who's lined up with the state and against the state, you're going to mostly see Republicans lining up with Wisconsin and Democrats lining up against the state of Wisconsin in favor of the plaintiffs. But there are exceptions, and an interesting one is John Kasich, the governor of Ohio, who is not a liberal Republican. He's a conservative man, but for whatever reason, he is pretty hardcore on gerrymandering just being a bad thing. And so Ohio has passed, and I believe Kasich has now signed, a bill introducing an independent redistricting condition in Ohio. So So I think we'll see how that plays out, and I don't know all the details, but I know that sort of the people who think about this stuff are pretty pretty psyched that this is happening and think that it sort of really does emphasize that this is kind of like, in principle, a kind of bipartisan good government kind of enterprise. So I think everybody will be watching Ohio to see how they set it up there and how well it works. It's definitely, I think it's definitely politically possible, and I think people will like it better than just having like endless court battles where the legislature draws something, they get sued, they draw something else, they get sued, like et cetera, et cetera. So. But we got to do more voting first.
So how much does it matter that n equals 2? I mean, some countries have n equals 1, and they have elections, but and
it's
we have
so much simpler.
We have n equals 2, and so what if it was 3 or 4? Has anyone done analysis of that? Because what I'm getting to is the idea that you know, that seems as though the kind of the polar opposite ends of the two parties that seem to be the greatest influence, and there's sort of a hollowing out of people in the middle that are what one would call more moderate, whether it was on a Republican or a Democratic side.
So it's a great question. Like, electoral politics works different ways in different countries. So I would say, if you look at countries where there are a larger number of parties with serious representation, I think they tend to not use the kind of geographic district model. So if you look at a country like Israel, and if you look at Israeli politics, you'll just, all of your complaints about the two-party system will just like melt away, and you'll be like, oh my God, thank God there's only two parties. No, it's like, no, but it's a very different system. But there, I mean, in a lot of countries, what you have is a proportional list where there's no geographic district, and just if a party gets 5% of the votes, they get 5% of the seats. And that's like a very different system from the one that we have here, right? So here, but I'm not sure you're thinking of like major and minor parties. You're like, what if there was just 3 parties that were all pretty major? How would this work? Is that?
Yeah, exactly right. Suppose the political spectrum was divided into
Yeah, so I think the model, probably the best model there is Canada, which does have geographic districts and which doesn't have as strict of a two-party system as we have. I think they have the 2 biggest parties, but in some sense there's sort of 2 center-left parties, right? The sort of Labour and the NDP, and there's also the kind of Quebecois party, which is sort of its own geographically based thing. I think it's more complicated. Obviously, honestly, I'm kind of punting because I'm like, okay, how do they do I have no idea how they do districting in Canada and like whether they have these same. Yeah, well, okay, so maybe one response to this is if you wanted a system that would take that wouldn't sort of like lock everything into just 2 parties and 2-party platforms, one way people talk about this is like, okay, what if districts were just a lot smaller and there were a lot more of them? Right, so I mean, you would certainly you could sort of carve out sort of like 1,000-person districts in the east side of Madison, which would have like much more left politics than like any statewide elected Democrat in the state, right? And they would like represent truly different points of view. And there's like lots of different places. I mean, you can imagine all kinds of parties that would garner support in like small enclaves like that. So that's the thing. There's kind of a crazy businessman in California who's trying to like push a statewide referendum that would make California have 15,000 state legislators. I don't think he's going to succeed. But I mean, it's exactly with that idea, right? So as you say, in the limit, as the districts get smaller, more different points of view are represented because it's easier for somebody whose point of view is not heard by the existing Democratic and Republican parties. It might be hard to win in a district of 20,000 like an assembly district or 60,000 like a Senate district that's like big. On the other hand, you know, I wrote something about this and then I got an email from like a kind of relative of mine who or the mom of a relative of mine who's in the who has served in the New Hampshire State House. So I don't know if you know about this, but the New Hampshire State House has 500 people in it. And New Hampshire is not a very big state. So that's kind of the model, right? So there is one place where it's happening where if you're just like popular shopkeeper in your small town in New Hampshire. You can be in the state house because the districts are very, very small. And what she said is it sounds good and it sounds like democracy, but then, you spend the first 6 weeks of every session being like, okay, should New Hampshire secede from the United States? Like that same crazy guy brought it up again. He's the legislature, just like all of us, so we have to debate it and we have to discuss it. And now somebody else wants to discuss whether we should cancel the state bird, and somebody else wants to discuss like whether all liquor stores should be closed on Tuesdays because that's what their religion says, or whatever. So I think there are efficiency problems, and I think at least my friend who served in the State House in New Hampshire says they're pretty serious. So I don't know how to square that circle. I'm just, those are my thoughts. Yeah. Oh, your mic is coming.
Two things. First of all, the science fiction story where a man goes back in time, steps on a butterfly, changes the whole world when he comes back. In terms of predeterminism, whether if you knew all of the variables, like in weather, would you be able to predict far into the future? That's one thing. And the second thing is, some districts probably have a lot of children. What's the fairness about that? I mean, obviously that was the decision that was made, but if you have a section that maybe is large Catholic or something, they may have disproportionate.
Okay, yeah, so 2 questions. One, reminding us of so in some sense, like the original version of this story where somebody goes back in time, steps on a butterfly, sort of changes the results of an election in the present. Could we, in principle, predict the effect of stepping on a butterfly like 30 million years in the past? Not a chance. But it's science fiction. What can I say? It's like physically impossible, but no way could we actually predict that. Okay, ready? There must be some mid-century science fiction fans in the audience who can name the title and the author of the science fiction story in which a person goes back in time, stamps on a butterfly, changes history. And I think so too. I'm not sure of the author, but I think it's Bradbury. Title, this one I know. A Sound of Thunder by Ray Bradbury. Okay. Then again, apparently I got Dick Cheney wrong, but I think I'm right about I was told that it was really Donald Rumsfeld, not Dick Cheney, who said that thing about it. Okay. Oh, as to the kids, all I can say is I don't think there's a right answer. It's the way we do it. There are districts in the northern part of Wisconsin where the median age is over 50. So there are definitely big differences in like how many citizens below voting age there are in the different districts. And well, it changes the percentage of people who will vote because not only is it that people under 18 can't vote, it's that people between the ages of 18 and 35 don't vote. So, it's this building that's deciding like who our mayor is and like stuff like that. I mean, that's how politics works here.
You've indicated that you have a child or children. What's your thoughts on the way they're teaching math in school now, for you being a mathematician?
Great question. So the question is, what do I think about the current teaching of math in school? So my oldest is a 6th grader, so I'm only just starting to get grumpy about this topic. I would say on the whole, it's an incredibly hard problem. I would say on the whole, I'm more positive than negative. There's been some teachers I've liked more, some I've liked less. Now, again, because my oldest is a 6th grader and just started middle school over at Hamilton, I have not seen that many teachers who are math teachers per se, right? Because in elementary school, you have your teacher, and your teacher teaches you everything, so there's not a specific math teacher. I think I would say I'm more positive than negative. I would say the materials I see come home with my kids, I think there is some effort to kind of not have it be purely by rote and have sort of questions that challenge the kids. One thing I was impressed by is that in kindergarten, when my oldest was a kindergartner, they kind of had the kids go around and do surveys like, what do you like better, like cats or dogs, and they sort of marked on a chart and made a bar gram. That impressed me as the way that they were thinking about how can we help kids think mathematically who can't even read yet, right? How can we, in a pre-literate, before there's literacy, we can still do mathematical thinking of like doing a survey and sort of ticking boxes and making a bar chart and sort of understanding which is given more frequently than that. So overall, like, Madison has just adopted, I'll say this, Madison schools have a tradition of autonomy, which overall I think is good. In other words, the tradition here has been that we give teachers, individual teachers, a lot of freedom to teach the material the way they see fit. And we have not traditionally locked math teachers into a curriculum. I think that has pluses and minuses. I think as a teacher myself, I wouldn't like it if like the Board of Regents was sort of telling me exactly what I had to do each week in my calculus class. It was like, this is the lesson you will teach and this is the test you'll give. Just wouldn't like it. I think I can do a better job like looking at the students in front of me and sort of understanding what their needs are. But we do have challenges with equity, where students who move a lot, right, because it's the poorest tranche of our students, the people who are socioeconomically disadvantaged, who tend to move from school to school. If each teacher is doing a different thing, that creates major problems for kids who move. So I do think we're trying to move more towards a somewhat more standardized curriculum. Not that each teacher is just a robot, but that at least there's some sense that if you go to 7th grade in one school and 8th grade in another school, you're not completely off the train, which I think is really a serious concern. I don't know, is that a good answer to your question? Those are sort of the things I know about as we think about math teaching here.
Any more questions?
Can we switch from politics and education to the movies?
Great.
I'm hoping you can tell us about your experience as both an actor and the math consultant in the movie Gifted.
Oh, of course. I don't know if any of you guys saw this movie, but there's a movie out called Gifted. It's about a young girl who's extremely advanced in math. The director of this movie, Mark Webb, grew up on Monroe Street, about maybe like 4 or 5 blocks from where I live right now. So he's a Madison guy and a pretty famous movie director who like mostly directs like kind of like $300 million blockbusters with Spider-Man in them, but like sometimes makes a sort of smaller, more indie type movie. So I got involved with this movie in a somewhat random way. It was that I had written an article in the Wall Street Journal about kind of child prodigies in math. So when the director and the producer were doing their research, just as they were getting ready to shoot the movie and working with their actors, I kind of just had a phone conversation with them, just as they were sort of trying to be like, well, let's talk to people who have had this experience, and get a sense of like, as a director, he wanted to know like, what am I going to tell my actor? And then we talked, and then he floated the idea of, well, we're doing this scene where there's going to be a lot of math on the blackboard. We kind of want somebody to be on set to make sure everything is right. And then, so he asked me to do that. But then he was like, well, there's this other scene where there's going to be somebody on stage for a few seconds doing math. Like, why don't you just do it? So I wasn't brought in because of my acting skills. I was sort of brought in as a consultant, and then since I was like there on the set, they were like, why don't you do it instead of just having an extra do it or something like that. So but I learned that legally, I'm not an extra because I talk. So if you talk, you're not an extra. So I'm on the IMDb. If you go to the page, I'm an official member of the cast because I talk. So this is the big separation between. So it's a funny business. Like if you're on the set, there's all this like. It's even more rigid hierarchy than there is like in a university. There's like the extras, and then there's the talent. Did you know that's what it's called? And the talent gets like a different buffet than the extras get, and it's all. Anyway, that was what but it was it's a very interesting enterprise. You really realize. Okay, I'll say 2 things that I didn't know that I learned from being on the set of this movie. One, movies are incredibly complicated and hard to make, and if you sort of see me like talking for like. Maybe 6 seconds might be an overestimate for like how long I'm talking. It's like very short. That's like probably 4 hours of work for about 35 people. It's like super crazy. You sort of stand there and you do it many times. You do the same thing many times. And if you mess up, and when I say mess up, by the way, I don't mean flub a line, because they gave me a script, and I like learned the lines, and I was like, very proud of myself. I practiced them a lot, and then I got there, and the director was like, oh no, just like say it however you would say it. Like, I don't care if you say the lines that are in the script. So I was like, but I worked really hard till but what they do care about is, you're standing there and you're talking, and you like put down like, the whiteboard rag, and then they're like, cut, you gotta stop because you put it down in the wrong place. You have to put it down in the exact same place every time because they're gonna intercut like from all of those 30 different takes. And I'm like, you really think somebody's gonna be watching your movie and they're gonna be like, oh, in the 2 different shots, the rag is in a different place. And he was like, yes, like people will notice and will get dragged, and like, so they really care about stuff like that. So I'm like, okay, I'll do it again, and I'll put the rag in the right place. The other thing I would say is that I had a stereotype that like child actors were like the worst people on the face of the earth. And actually the star of this movie, who I think was about 11 when it was being made, was like the most like insanely on-task, professional, together child I have like ever seen. Which in retrospect I should have understood, because like, I mean, I'm sorry I love my 12-year-old, but like, he couldn't like work 8 hours a day like making a movie. Like he would like wander off and like get grumpy. I mean, like, so I think actually, so now I think like child actors are like extremely professional, like very together people who are great. So that's my thoughts about the movie.
Was it a good movie?
It's a pretty good movie. It's always, I'll say this, it's like always on the plane. Like almost any plane you go on, it'll be on the plane. Because it's exactly that kind of movie, you know what I mean? It's like very heartwarming, it's not too long, like it's like, and so at least twice already, this happens a lot, like I'll be on the plane and the person next to me will be watching it, and I'll be like, I'm in this, wait till the end. Well, wouldn't you? Like, how could you not? And it's at the very end, so I'm like, wait till the end, because they think I'm kidding. I'm like, wait till the end, you'll see I'm in this.
So I've been wondering, with these 10,000, this is back to the maps. With these 10,000 versions of the maps that they draw of Wisconsin to sort of try and balance the electorate, aren't they all quite similar? Or do they see a pattern in this? Has anybody really looked at that? And I mean, you would think that there could be some way that there would be ways of looking at all of those maps and the patterns that they have that could inform the way that the districts are drawn.
Yeah, you'd think, but no. So basically, they don't look that alike. There's a huge number of ways the maps could possibly look. You should think of it as like, how many possible chess games are there? Like, there's a lot, and no human being can like think of them all. You somehow have ways of like thinking about like the most reasonable ones, but even there, like good chess games can look very different from each other. And so, but this is an empirical question, right? It's not obvious until you do the experiment what it be, but in practice, yeah, those maps do look pretty different from each other, and there would be like tons and tons of radically different looking fairways. I mean, even look at how much, I mean, if you even look at like how much the Act 43 map that we use now differs from what came before, you can draw a lot of different maps that meet the rather modest legal requirements for what the map has to satisfy. Okay.
Any more questions? Okay, Jordan, on behalf of the UW Retirement Association, and in lieu of your honorarium, we have a small token here.
Oh, thank you so much.
A pillow with a blanket.
Oh, that is awesome. Thank you. I can't help notice you took it out of an Ohio State bag. What's going on with that? But then it has a, then it says Wisconsin. The bag says Ohio State. I was like, what's going on? But then it says
Big
Wisconsin. So that's okay. Okay. Thank you guys so much for coming.